invitation to this conference and have opportunity to present my results not only to Kyiv and world community, but also to Lviv, because you know that all these reforms concern not only Kyiv University, our chairs also were unified back. So there was time when I started to work in at CAF chair of algebra and topology, and then it was divided into algebra and logic and topology and geometry, and now we have synthesis back to chair of algebra, topology, and foundations of mathematics. So that is the name of the chair. I'm happy to represent this new chair. The head of the chair is back, Mikhail Zarichny, as was years ago. Concerning collaboration with Kyiv, we have very nice, basically, history, and present time also is very good. In history, I remember that Kravchuk, academician, he was mentioned in the talk of Professor Petrovchuk. He very often visited Lviv in pre-Soviet times. So he published, for example, good papers in Zapeski of NTSH, published it in Lviv, and with Kyiv algebraists, we very often meet in summer schools with Protasov. We permanently write some papers, so I was satisfied with collaboration with Kyiv mathematics and hope that it will last forever. So my talk is also of such general nature. It is topology in arithmetics. So I will talk about 2 or even 3 interesting topologies on natural numbers. So natural numbers, it is basic object for whole mathematics, and you know that Gödel encoding can encode all mathematics in natural numbers. So it's a fundamental object, and it also carries some topologies which is not so commonly known. So I will recall those 3 topologies on the set of natural numbers. The first one also chronological, was introduced by Furstenberg in 1955, so it is already 65th anniversary of this topology. It is generated by arithmetic progressions. In natural numbers, we consider progressions of the form a plus bz intersected with natural numbers, and such a progression is declared to be basic open neighborhood of this topology. I will talk about this topology later, but now it was introduced by Furstenberg when he was 20 years old student of the university. So he just remarks such remarkable thing for the proof of Euclid's theorem on infinitude of the set of prime numbers. And the second topology was introduced by Golomb. It's also very, very interesting person. 4 years later, he observed that this Furstenberg topology contains sub-topology, which is generated by arithmetic sequences for which there is restrictions on A and B. So those A and B should be relatively prime. So the A and B have no common divisors. And still weaker topology was introduced 10 years later by Kirch. Kirch also is American mathematician, not so known as Furstenberg and Golomb. So his topology also is generated by arithmetic sequences. And this time A and B must be coprime, and also B is square free. That means B is not divided by the square of a prime number. So just product of some distinct prime numbers. So we have such 3 topologies. It is clear that, oh, sorry, here there is mistake, vice versa. So the smallest topology is Kirch, then there is Golomb, and the largest one is Furstenberg. So it must be K and F replaced by their places. Those topologies are second countable. That means they have countable base of topology. It is clear because the number of such arithmetic sequences is countable. Parameters run over countable set. And they are Hausdorff. How to see that? If you have two distinct numbers, you just take a large prime number greater than x and y and consider such two arithmetic sequences. And those arithmetic sequences, they do not intersect. Okay, so this Hausdorff second countable. Now, I cannot mention about Furstenberg because this year he was awarded by Abel Prize. It's very important prize in mathematics. 35 in Berlin, but 35, you know what happened in 33. So he escaped from with his father to New York and so studied in New York in some Jewish university in New York. It was Yeshua, probably, and in this university he invented his Furstenberg topology. The Solomon Golomb is even more interesting person. He was also born in 32. His descendants are from Litva, and some Russia. So he also finally was settled in the United States, and he's example of very universal mathematician. He's known for the most used computer algorithm. It is a maximal length shift register sequence. So this is his invention, which is used all the time in all possible coding devices. So this is a generator of pseudo-random sequences, basically. But he also did popularization of mathematics. He has a column in Scientific American, and he studied number theory and games. Also, he invented polyomino, such game, which inspired creation of Tetris. Remember these times when everybody played Tetris in 80s. So this is a very good example of mathematician. Each mathematician should be like Solomon Golomb, be simultaneously popularizer of mathematics and good theoretical mathematician, also have application in computer science. Everything done by Solomon Golomb, and he also introduced this Golomb topology. So not introduced. It's also interesting story. The Golomb topology was introduced by Brown. So this is typical situation when the notion is named not after the inventor. Brown in 53 introduced this topology. Published a very short paper in Notices of American Mathematics, something like this. It was just 1/3, less than half of page. So definition of this topology and important property, which means connectedness. And then Solomon Golomb, he was studying number theory, and he was so excited by this topology that he went to Toposim, this first topological conference in Prague in 61st year, and he advertised this topology very strongly on topologies in order to convince them to prove Dirichlet's theorem. I will say about this on the next slides. Okay, about Kirch, not so many known. Who was that mathematician? Okay, and all these three topologies, Furstenberg, Golomb, and Kirch, can be used in a very surprising topological proof of theorem of Euclides, which is just 2,000 years ago and more. So there are infinitely many prime numbers, and I will present its very short proof. Surprising. So take one of these three topologies. It can be either Furstenberg. So the initial topology was Furstenberg. So Furstenberg invented this topological proof and became famous in 20 years, being undergraduate student. So take one of these three topologies on natural numbers and let us observe that such a arithmetic progression starting from 0, so all prime number, it is closed in all three topologies. It is closed in Kirch topology, which is the weaker one, and then in all other, because if you take any x which is not divided by p, you can consider this basic open neighborhood of x, and it does not intersect this set Pn, which means that Pn is closed. Okay, each point from outside can be separated from the set by the neighborhood, so it is closed. And if we assume that the set of prime numbers is finite, we can consider this finite union of closed sets. Okay, it is still closed set. Finite union of closed is closed, but this union is all numbers except for one, which is has no prime divisors. So this union is everything but one, and then one is open set. But all open sets are infinite, because arithmetic progression are infinite, and that is contradiction which gives you the proof of topological proof of Euclid's theorem, and this is basically the first application of topology in arithmetics due to Furstenberg. Okay, so now let us look at this Furstenberg topology. What is clear that it is second countable, and Hausdorff, you already know this, and it is also zero-dimensional. Zero-dimensional, it has base of closed and open sets, because these arithmetic progressions are simultaneously open and closed. Closed because it's the complement to this sequence is finite union of such the same sequences shifted. Okay. So it is zero-dimensional and is countable, second countable, zero-dimensional, so it's regular, has no isolated points. And there is a classical Sierpinski theorem which says that any such space, countable, second countable, regular, without isolated points, it is a copy of space of rationals. Rationals also countable, second countable, no isolated points. And this implies that natural numbers with Furstenberg topology, they are homeomorphic to rationals, and as a corollary, they are topologically homogeneous. So any points can be replaced by any other points by homeomorphism. And it has large homeomorphism group of cardinality continuum because rationals are very homogeneous. They are not have shifts, only shifts. Each bijections between integers can be extended to homeomorphism of rationals. It is easy to see, but this shows that there are many homeomorphism of Q, continuum many. Okay, so what can be said about Golomb and Kirch? So Furstenberg was homeomorphic to, is metrizable basically, homeomorphic to rationals. And in case of Golomb and Kirch topology, now we have that this basic open set is not closed anymore, it's just open. And the closure of this set contains arithmetic progression starting from 0. Okay, why? Why? Basic open set, take closure. So let us take any point from this progression Bn, and we would like to prove that this x belongs to the closure. This means that any neighborhood of x should intersect this set. Okay, so take neighborhood of x. This D must be coprime because it is Golomb or Kirch, coprime with x. Okay, and since x is divided by b, D is coprime with b. They have no common divisors. And you can apply another classical theorem in number theory, Chinese remainder theorem, and find here in intersection something. So this two arithmetic progression have non-empty intersection because those numbers are coprime. And this means that the neighborhood of X, this one, intersects this open set, and X is in the closure. Okay, what does it mean? That the closure of any open set contains such a arithmetic progression starting from 0, and any two progressions starting from 0 intersect. You see, so Golomb and Kirch topologies, they have this very interesting property. So for any non-empty open sets, U1, Un, here you can find arithmetic progressions. If you take closures, in those closures there is an arithmetic progression starting from 0, and any such arithmetic progression have non-empty intersection. So this intersection also contains arithmetic progression starting from 0, so it is not empty. So this space is connected. Any open set, any closures of two open sets, they intersect. And if space is disconnected, this means that it can be decomposed into two open disjoint sets, and the closure, each of these open set is closed simultaneously because it is complement to the open set. So in disconnected spaces, there are open sets with disjoint closures. And here we have opposite. So it is connected, and even what is called superconnected, this is just this property. Okay, so Golomb space, it is example of countable, second countable, Hausdorff, and connected space. The first space of this form was constructed by Urisson in 26. It was difficult construction. And this one is very simple, and this property was exciting Golomb so much that you have such a simple example of natural numbers, connected space. Okay, so this is the same theorem that Golomb and Kirch are connected, and definition of connected. Connected, the space which cannot be written as union of two disjoint open sets. Non-empty superconnected, this is this property. For any non-empty open sets, the intersection of closures is not empty. And locally connected space, the space that has a base of topology consisting of open connected subsets, like real line, for example, or the plane, it has base of topology consisting of disks. So the spaces, natural numbers with Golomb and Kirch, they are countable, Hausdorff, second countable, and connected, even superconnected. We can ask if those spaces are homeomorphic, because Furstenberg is metrizable, so it's not homeomorphic to these two. And the answer is no, because this is the reason why Kirch introduced this topology. So the Kirch topology is locally connected, Golomb not. So they are topologically distinct. Okay, so we have three spaces, Furstenberg, Golomb, Kirch. They all are pairwise non-homomorphic because Furstenberg is metrizable, and those two are connected. And two spaces, Golomb and Kirch, are not homomorphic because one of them is locally connected, the other is not. And we have also this theorem, which also excited Solomon Golomb, theorem of Dirichlet. It is a difficult theorem in number theory, which is proved using analytical methods. So it is not elementary. It uses some complex analysis. So theorem of Dirichlet says that in each arithmetic progression with coprime A and B, there is a prime number. So prime numbers are just in any such progression, which means in topological terms that the set of prime numbers is dense in Golomb space and in Kirch space. It is dense subset. Each open set contains prime number. For Furstenberg topology, it's not true, because, for example, such arithmetic progression, 4 plus 8z, it does not contain any prime number. Okay, and this problem was posed by Golomb on the first toposim. Can Dirichlet theorem, this which is proved using complex analysis and analytic number theory, proved topologically? Because this theorem is topological by formulation. Prime numbers are dense in the Golomb topology. Okay, is there topological proof of this topological fact? Okay, and this is still open problem. Nobody knows how to get this topological result from topology, pure topology. Okay, and now some results about Golomb and Kirch topologies, because Furstenberg is topologically is clear. It is our joint result with Professor Miduszewski and Turek. Miduszewski, he now 93, sorry, he's very old. 93. Miduszewski, he is classic of topology, and he was present in Toposim in 61st and listened to the lecture of Solomon Golomb. That is why I know about this problem. So there is a historical line like Erdos number, you know. So Solomon Golomb arrived to Prague in 61st. Miduszewski listened to his lecture and he knew about this problem. Turek was pupil of Miduszewski. And I worked with Turek in Poland in the same university. So this knowledge is spread in this very strange way. So we published in 2018 this theorem as a paper containing this, that prime numbers in Golomb topology is metrizable. It is dense metrizable subspace. And these prime numbers in Golomb space is homomorphic to rationals by the same Sierpinski's theorem. Golomb space has many continuous self-maps, so it is connected and has continuum semi-group of continuum self-maps of the Golomb space is large, has cardinality of continuum, but this is next result with Italian mathematician Spirito. But the homeomorphism group of the Golomb space is trivial. What is strange? So this space, unlike to Furstenberg, which has a lot of homeomorphism, the Golomb space is rigid. This means that somehow topology feels divisibility. You know, that numbers are somehow these number theoretic properties influence on topology in very strange ways that make this topology rigid. And the same is true for Kirch space, and this is just very recent result of me and my postgraduate student Stelmach. This is our joint talk with Stelmach. Okay, and if I have no time, I can stop at this moment, but I still have 5 minutes. So this main result, mainly those rigidity of those two spaces, and maybe several words about how to prove that. The proof is not simple, and I cannot explain this in one seminar talk, but maybe idea. The idea is to investigate a so-called superconnected poset. So when the space is superconnected, we can consider such a filter. Okay, so consider this filter of sets which are larger than intersections of closures of open sets. Okay, we know that such intersection is not empty. So such all possible intersections, they form a base of some filter. This filter is called superconnecting filter, let us say. And the filter contains many subfilters. For example, we can fix a finite subset of this superconnected space and consider the filter which consists of here, sorry, copy paste. It must be here x and x here. So the intersection of neighborhoods of some points in fixed finite set. So they are subfilters of this F infinity. And we can form such a poset, this largest filter and subfilters. And this poset has partial order. This is largest one, this smaller, and maybe there is some order relations, and each homomorphism of superconnected space, it induces order isomorphism of this poset, partially ordered set, and analyzing the action of homomorphism group of this poset, we can just derive that there is no homomorphisms. So here there are some explanation how to prove. So it's already how to prove this rigidity. So I will skip this because I have no time. There are some ideas, but not whole the proof. It uses many fantastic results of natural theory of numbers. For example, Mihailescu theorem. It is bomba. Okay, it says that there are only two consecutive powers. 9 and 8, there are only two powers of numbers that differs in one. This Catalan conjecture. So we use and Mihailescu here and Mersenne primes and Fermat, everything, all Zygmunt also this nice theorem from 20s, which is used for the proof of these topological facts. And here other papers where everything is written. This is with Meduszewski-Turek, with Spirito, rigidity of Golomb space, and this last one about Kirch. So maybe I will end at this point, and if you have any questions, I will be happy to answer. Thank you.